Hi and welcome back. Today is May 4th, 2020. May the 4th be with you. Today we're showing off the video odometry program. For this, we take in a video provided by Oxford. Obviously, links will be down below so that you can check out the code. And we're showing off the ability to use stereo vision to track a car's movement by checking out matching positions from a screen from one frame to the next frame, and then disambiguating that through a bunch of different math. This includes creating the fundamental matrix, finding the essential matrix, disambiguating the pose, triangulation, etc., etc. Once again, check out the code in the description below if you're really interested. This project was really cool, although it was really difficult. If you do check out my code and you figure out what the hell I did wrong, I would love for you to leave a comment down below. But let's go ahead and get into this. So, as always, we just have this. The first thing that's going to come up is if you want to create a data set. For us, we decided that to save on time, because it would take about another 2 hours, depending on how we ran this, to create the data set. And all we're doing for this is that we're finding the intrinsic parameters of the camera, and we are also making all of the frames into grayscale frames, and we're also undistorting them. So we opted to make this its own process. If this is the first time that you're running this program, you will have to enter yes, but since I already have this, as you can see it's right here, we're just going to go ahead and hit no. Once again, we need to locate the directory. My example is the default one, so if you just hit enter, boom, we have our thing loaded. I also put in the option to skip running things because, once again, it takes a long time to generate all of the frames and all of the points that correspond to them. So we ended up saving off any run that we do as a pickle object. Let's see. Oh, I need to go back to here. As you can see, we have save var, list pose, save off, and this saves off all of the poses that have been used. So just to show off the process a little bit, we'll go ahead and hit Y. As you can see here, we've got two different windows. On our left window, we have the custom function and the OpenCV function. Both of these were generated using our code. Then we have our output. We'll go ahead and let this run for the duration. So as you can see, we've been following for about half the video now, and we've gotten 2 turns on the OpenCV function that are functioning pretty darn well, but as you can tell, not so much for our custom function. And we've tried out a bunch of different things, and we think there's some issues when it comes to selecting points in the fundamental matrix. We are using a ransack formula, however, it doesn't seem to quite mirror what we're getting in the OpenCV functions that we use as a baseline. So we end up getting a bunch of different issues with the geometry. One thing that we did notice is that when we do the testing in a segment, so we do a very short bout, like about around say this turn that we're about to do, or this turn that we did up here, or this turn that we did up here, we are actually able to get really good results. And those are going to be, once again, in the report in the link down below. But we'll just go ahead and let this finish out. Yeah, so we can see from that image that we were able to get decent. It was decent. It wasn't fantastic as compared to some of the spaghetti that we had been getting before, or even points that would just randomly generate throughout the map. But why don't we go ahead and take a little bit of a look through the process on how we did this. So our pipeline here is, first we get all of the information, declare our initializations, we create a sift object, we then start our program and start it from frame 19 and go to the end minus 10 frames. This was done as those last 10 frames were essentially sitting in the same position, so we're not all too worried about them. We then run through everything and check every 50 frames. If you want it to run just a little bit faster, you can change this to be whatever you want. Obviously, if you go higher, then, like say you make this 150, it'll actually run a little bit smoother. It'll print off estimated time till completion, and then it'll also show you progress as you're going. If you see here, this is our custom function. You'll see that we did this with a bunch of our stuff. And so we'll find our matches between the previous image and the current image using our sift object. This will generate the points. These points then go into our compute F matrix, which will ransack an F matrix and output the F matrix, or the fundamental matrix, along with points that are inliers. We can go ahead and take a little look at that. You can see here, we get random 8 points, we make them homogeneous. The ones that aren't homogeneous are created in a fundamental matrix. From this, we'll normalize them, place them in an A matrix, solve the linear equation, and then enforce the rank, denormalize, dot this product again to get our F matrix, and then we'll enforce the rank by dividing by the last element. We then spit that out. It goes into our ransack program. We find the error by, once again, computing the same equation, x2t dotted with fc dotted with x1. And if those are inliers, it will create a mask. And then once we have those values, we'll export them, and and then use those values to actually create our F matrix one last time, and we'll enforce the rank. Now, I'm not going to go into everything on this. Obviously, there's a lot that goes into it, but it's nice to go through some parts of it. Next is the essential matrix. Once again, this is inside, where is it? On camera pose. Central matrix. So really, a lot of this is just assertions. This is Chang's way of doing it. For the most part, most of the stuff comes from solving the linear equation and then dotting things again. Not all too difficult. And then we get to the triangulation aspect. Once again, well, this video is starting to get a little bit long, since it's really just to show off our process. Then it disambiguates it. And once we're done with that, we homogenize the transformation and rotation into a form that we can use to grab the XY coordinates and append that list, and then restart it. And we can go ahead and run that. We'll do the first 30 points using the OpenCV stuff, or actually we'll do the first 30 points using our custom function, just to show that off. Once again, we'll hit no, we'll hit enter, we'll hit no, and then we'll hit no. As you can see, it approximates that it's going to be about 5 hours, and we're starting. And as you just saw, a little bit of progress came up after we finished entering the 3 poses. It took about 3 minutes, and obviously we're not going to wait around for all 50 or all 3,700 plus images to render. But thanks for watching, and that was our project. Stay tuned for more projects and subscribe if you want to follow along. Bye!